Hello, everybody. My name is Austin Sumner, and I'm very glad to be presenting my honors thesis in the Fall 2020 Honors Symposium. My topic is dynamic loading experimentation and surface imaging of pressure vessel load cell fractures. Here's a brief overview of how I'm going to structure this presentation. As this thesis has two overarching topics, I'm going to talk about the first one first, which is wind experimentation, and then I'm going to move on to the second one, surface imaging, and I'm going to cover all applicable information for this thesis within the time period allotted. Starting off with background of pressure vessels. Pressure vessels are used extensively throughout the industry. These pressure vessels in particular are used in the oil and gas industry to hold catalyzing chemicals. There are only a few important geometry points that I want to talk about, the first of which is the manway. The reason the manway is important to think about for this research is that it shifts the center of gravity of the pressure vessel itself. Without the manway, the pressure vessel cross-section is relatively symmetrical, and the center of gravity would be centralized to the body. With the manway, this center of gravity is shifted, and this is very important for this research. The second major geometry part is the parallel bars. Parallel bars are very important for the structural stability of the pressure vessel, as they hold the legs together and reduce vibrations when a heavy wind loading or heavy dynamic loading is striking the vessel. And finally, the pressure vessel sizes. Throughout this research, 3 pressure vessel sizes were tested for instability: a 50 cubic foot, a 200 cubic foot, and an 1100 cubic foot pressure vessel. Here, some of the major dimensions and weights of the vessels in different fill conditions can be viewed. Now moving into the theory of this project. The reason that this project is being performed is to provide an understanding of how wind will cause a weight imbalance in these pressure vessels. The theory is that when a heavy enough wind load strikes the pressure vessel in its worst case scenario, the wind will actually cause the pressure vessel to become imbalanced. This worst case scenario is illustrated in figure 2 here, and it is when the wind is moving in line with the manway, effectively pushing the pressure vessel more in the direction of the shifted center of gravity due to this manway placement. In order to create an experiment with this, a dimensional analysis was performed. Dimensional analysis is a process in which engineers can take very large and complex tests and scale it down using smaller, more controlled models by modifying one dimensionless number. And for this experiment, the Reynolds number was modified, and different wind speed values were calculated that are proportional to the toppling wind speed values within a larger pressure vessel geometry. Additionally, dimensions for scaled down 18-inch tall models were found, and those 18-inch tall models were created and shown in the slide. The reason we went with 18-inch models is because we would like the center of gravity of that 18-inch model to be somewhat in line with the center of flow of the wind tunnel. So Georgia Southern University has a subsonic wind tunnel that is capable of producing laminar flow up to 30 miles per hour, and it has a mouth of 24 by 24 inches. Additionally, in order to perform filled tests along empty vessel tests, a mass replacement was needed. To be as realistic as possible, the volume for filled tests needed to be proportional to the filled volume in actual pressure vessels so that the center of gravity was proportional to the filled vessels. This table shows the required densities and masses that needed to be added to the 18-inch models so that the tests could be run. In order to achieve these densities, a mixture of powdered carbon and styrofoam was used to get the appropriate volume and mass requirements for the vessel so as to not shift the center of gravity vertically at all, but to add a proportional amount of weight. Getting into the methodology for the wind experimentation, the first step was always preparing the vessel for whatever test was being run and finding experimental toppling values through trial and error. The wind tunnel was then set and wind speed values were taken at 6-inch intervals using an anemometer. Then the pressure vessel was placed in the testing region shown in figure 6 and rotated at every measurement spot in 6 different orientations. The pressure vessel only ever experienced instability when it was in the worst case scenario depicted earlier. Toppling values were then found and recorded to be compared to the theoretical toppling values found using the dimensional analysis. And here are the results. Analysis here shows that the added mass in the catalyst-filled tests increases the structural stability of the pressure vessel models greatly and allows it to take more wind loading before toppling would occur. The theoretical and experimental values both agree with that. After experimentation, the percent errors between the experimental and theoretical values were calculated. Additionally, the actual wind speeds that would topple a large pressure vessel are shown below in Table 8. There is a visible increase in the wind loading required to cause instability when the added mass is being put into the pressure vessels. Now, this is the second half of the thesis, surface imaging. I'm going to start off with a few important pieces of information about load cells and their configurations. Load cells are used especially in this application to find the amount of weight in a pressure vessel or similar body. The configuration of these pressure vessels in the field can be seen in figures 7 and 8. They usually rest as a connector between the base and the leg of the pressure vessel. The differently sized pressure vessels have differently sized load cells. For example, the load cell for the 1100 cubic foot is shown on top and it's rated for 40,000 pounds, where the load cell for the 50 and the 200 cubic foot pressure vessels are shown on the bottom. That load cell is rated for 5,000 pounds and 10,000 pounds, respectively, for the 50 and 200 cubic foot vessels. This research is being performed on load cells that were kept under pressure vessels in this configuration and experienced fractures over time. It is being done to support the dynamic wind experimentation and show how the imbalance caused by the wind on the pressure vessels will be translated to fractures in the load cells. Here are a few properties of the 17-4 stainless steel alloy that the load cells are all made out of. Georgia Southern University owns a VHX 1000 microscope with a VHZ20R lens and a VHZ500R lens. This provides a range from 20 times magnification to 3,000 times magnification. It has many surface image capabilities, including 2D and 3D depth scans. The 3D depth scans can provide accurate profiles of the area and show the depth of any surface. Here's some background on fatigue life. Fatigue failures are caused by oscillating applied loadings, such as a motor spinning a shaft or a pressure vessel constantly striking a load cell with a low magnitude impact. Fatigue life has 3 stages. Initiation is the first. It's where a crack begins to form due to an applied fatigue loading. Crack propagation is the second, where the crack will continue to grow due to the fatigue loading and corrosion or exposure to the elements. Finally, a catastrophic rupture, and this is where the geometry of the body is no longer capable of holding the loads that are being applied to it, and so it just simply fails. To start off the methodology, the first step was to prepare the specimen and the microscope and scan settings. This includes brushing off the surface if necessary, orienting the microscope to get the most in-view picture of the specimen face, and modifying the magnification, focus, and brightness of the microscope and optimizing them for the scan that was being performed. In this picture, the 2 load cells that were being imaged are shown. The one on the bottom is fractured all the way through, and the one on the top has a small surface cracking on the bottom of it in the same locations that the fractured load cell saw its fracture, right about there. The unfractured load cell on the top also has a very small surface crack on the other side of it that is not shown on the figure. It roughly is about right there. 3 major locations were identified for scanning. The first of which was the fractured face itself and is identified by the white circles on the screen right now. The second of all of these is the surface cracks on the unfractured load cells, shown right there, and also right here is the small one. And the final one is the contact region between the load cell bracket and the load cell itself to see how the wind loading is really hitting this load cell. The results of the fractured face scan show a few things. Firstly, as it is shown in the 2D scans above, there's a discolored gradient along the load cell face. This gradient is caused primarily by exposure to the elements. This is important because it shows how deep the crack had penetrated in stage 2 of the fatigue life until catastrophic failure was initiated. Another key takeaway that can be seen from these surface profiles is that this was a ductile fracture rather than a brittle, high-magnitude impact fracture. This is concluded because of the way that the profiles seem to peel apart from each other rather than shear off quickly. This is also supported by the fact that these fracture faces had no smooth, flat sections and rather were bumpy across the whole face. Brittle impact failures tend to have shiny, flat sections where the face just sheared off of itself due to a high impact loading, whereas ductile fractures are generally bumpy and rough and sort of peeled apart. The second scan of the surface cracks on the unfractured load cell are shown here. Figure 18 shows the small crack I mentioned earlier, and figures 19 and 20 are taken off of the long crack that spans the whole load cell. From the depth scan in figure 20, there's a 2.26 millimeter deep crack within the load cell. This means that the crack was well past initialization and was propagating until the load cell was removed from service. The smaller crack is 16 millimeters long, and it provides a good understanding of where the cracks are being initialized. And that is on the bottom side of the load cell towards the edge of the load cell's geometry. Finally, the scan of the contact region between the bracket and the load cell is shown. The key takeaway that can be seen from the colored depth scans is that there are many bumps and areas of obvious dynamic contact. This indicates the pressure vessel is actually showing instability due to the dynamic wind loading, and the instability is being translated onto the load cell in the form of low magnitude impacts, which are infrequent and random and contribute to the fatigue failures found. Here are the final conclusions being made about the surface imaging. First, all three stages of fatigue life are identified through the surface crack and fatigue and fracture phase scans. This includes the location of the crack initialization. Finally, the surface imaging of the contact region shows that the imbalance in the pressure vessel caused by a dynamic wind loading is being translated onto the load cell through low magnitude impact forces, which contribute to the fatigue failure we've seen. Here's a source I used in this presentation, and I would like to thank you so much for listening. If anyone has any questions or wants to know any additional information on these topics, I'd be more than happy to have a conversation and clear up any potential questions. My emails are on the screen right now, and you can always leave a comment on this video and I'll get back to you. Thank you so much.